Good afternoon, colleagues. Thank you, Art, Valerie, Katie, and Kevin, for arranging this thought-provoking workshop and also for inviting me to attend. Thank you. The academic home of Isaac Newton is a great place for any scientific workshop. And because this is the academic home of Newton, I have to begin with calculus, not of the dental variety, but its mathematical cousin. So, on to div, grad, curl, and all that. Let us think of a scalar as a tensor of rank 0 and a vector as a tensor of rank 1. The gradient transforms a scalar into a vector, thereby increasing the rank by 1. The divergence transforms a vector into a scalar, thereby decreasing the rank by 1. But the curl transforms a vector into another vector, and so the rank does not change. The rank of a tensor is independent of the number of dimensions of the underlying space. But we live in a world with 3 spatial dimensions, so we can view the curl from a dimensional perspective too. And for that, let me present to you a pirouette performed by a ballerina. And a terrifying tornado. Wow! Variations of a vector along 2 dimensions interact to produce a resultant in the 3rd dimension. And that you can see from the simple Cartesian expression here. The curl is key to understanding a fundamental aspect of life as we know it. Chirality. Some 20% of each one of you and me is chiral. Because in addition to water, our bodies comprise proteins and carbohydrates, which are chiral. Let us go back about 210 years. Jean-Baptiste Biot was a balloonist, mathematician, astronomer, and a researcher on electricity, magnetism, and light. Today, he is mostly remembered for the Biot-Savart law. But he also made a notable contribution to saccharimetry, that is, the concentration of sugar in molasses. Let me show you the recreation of an experiment that Biot reported in 1815. What you see here is a vertical polarizer on the left, an arbitrarily oriented polarizer in the middle, and a screen at the right end. Light transmitted through the vertical polarizer is vertically polarized, and a part of it passes through the second polarizer to hit the screen. Next, the second polarizer is made horizontal, so that only horizontally polarized light can pass through it. But the light incident on the second polarizer is vertically polarized, so there is no beam impinging on the screen. Next, a glass tube containing corn syrup is interposed between the 2 polarizers, and you can see a beam impinging on the screen. Finally, rotate the second polarizer to a specific position, and again, there is no beam impinging on the screen. This degree of rotation of the second polarizer depends on the length of the tube and the concentration of sugar in the corn syrup. Now see the experiment in full that was reported in 1815.
The transmitted beam down at the end. I'm going to set the polarizers So they're crossed and our beam is extinguished there. All right. And then I'm going to insert the cell into the beam and we'll see what happens. And when I do that, we can see, yes, suddenly we have transmitted light coming through it. Now let's see what's happened to the polarization. It goes in vertically polarized and it comes out at some different polarization, so it's, at least some of it gets through the cross polarizer over here. So if I rotate the second polarizer, I can see it looks like the polarization, the Caro syrup has rotated the plane of polarization about 45 degrees. Well, what happens if it looks like the light's rotated, clockwise, right? Gone from here to there. So what happens if I send the light through it the other way? Does it rotate 45 degrees the other way or not? I can take it out. I'll get back to our cross condition here. All right, and then I'm just going to flip the cell around and put it back in. All right, again, we see light coming through. Now, which way has the polarization rotated? And I can see, as I do that, that it looks like it's again rotated at 45 degrees clockwise. The transmit.
Notice that reversing the tube had no effect. Thus, the passage of light through the tube is reciprocal. Also, corn syrup is isotropic. How to explain? That was a big problem. By the time 1830 came, it was known that light obeys what we now call the Helmholtz equation. An exponential minus I omega t time dependence is implicit in this presentation, with omega as the angular frequency and t as time. In the Helmholtz equation, n is the refractive index, k naught is the free space wave number, and the vector u is the light vector. What the light vector is, that was not known. The solutions of this equation were, however, known. These are the three linearly polarized solutions for propagation along the z-axis. The first two solutions are transverse. The third solution is longitudinal. The longitudinal solution was ruled out by polarization experiments. From linearly polarized solutions, one could construct circularly polarized solutions, and these could have two-handednesses, left or right. Perfect. The light vector can rotate, but how can a material rotate the light vector? The answer to this question had to await the emergence of the Maxwell equations. Post-Maxwellian optics had different equations, but they did lead to the same expression for left and right circularly polarized light. And one more thing. The light vector is either the electric field E or the magnetic field H, both obeying the same relations in an isotropic dielectric magnetic medium with relative permeability mu sub r and relative permittivity epsilon sub r. The second order differential operator in this equation has a double curl term and a no curl term. We can factorize this second order differential operator into two first order differential operators, each of which delivers a Beltrami field. One of the two Beltrami fields is right-handed and the other is left-handed. For plane wave solutions, the right-handed Beltrami operator delivers right circular polarization, and the left-handed Beltrami operator delivers left circular polarization. The wave number in the right-handed Beltrami operator is k sub r. The wave number in the left-handed Beltrami operator is denoted by k sub l. In an isotropic dielectric magnetic medium, both wave numbers k sub L and k sub R are equal. So no rotation of the overall electric and magnetic fields is possible. Paul Drude realized that the two wave numbers must be unequal for net rotation of the electric and magnetic fields. The second order differential operator would need a single curl term in addition to the double curl and the no curl terms. And he got the single curl term by changing the constitutive relations. So here are the two Maxwell curl equations. They need constitutive relations. These are the constitutive relations of vacuum. D equals epsilon naught E and B equals mu naught H. For an isotropic dielectric medium, the constitutive relations are the same as of vacuum, but there is a relative permittivity scalar added, epsilon R. For an isotropic chiral medium, Drude added the curl E term with beta as the chirality scalar. And that was enough to get the single curl term in the equivalent of the Helmholtz equation. Optical rotation could therefore be explained through a phenomenological option. Simply modify the constitutive relations. But this medium is not reciprocal, in direct contravention of experimental findings that you saw earlier. To account for reciprocity, the same curl term must be added to the constitutive relation for B. This was done in 1959 by Fedorov. Frequency domain electromagnetic fields have been treated using Beltrami fields in a book I published in 1994, where you can find several details. And now on to elastodynamics. With U now denoting the displacement vector, we have the Cauchy strain epsilon as the symmetric portion of grad U and rotation R as the antisymmetric part of grad U. We also have the stress, which is related to the Cauchy strain through two Lamé constants, lambda and mu. This equation is a constitutive relation for isotropic materials. And then we have the equation of motion. Divergence of stress plus rho omega squared times the displacement equals 0. Here rho is the mass density and omega is the angular frequency. This equation allows the conservation of both the linear momentum and the angular momentum. Substitute the equation for stress followed by that for strain in terms of displacement. And as you all know very well, Navier's equation pops out. It contains a double curl term, just the same as in electromagnetics. Now, partition the displacement into irrotational and solenoidal parts. The irrotational part is denoted by U sub P and the solenoidal part by U sub S. The irrotational part of the displacement satisfies one second-order differential equation. The solenoidal part satisfies another second-order differential equation. This latter second-order differential equation is the same as in electromagnetics, and so we know that we can think of Beltrami fields again. The solenoidal component of displacement can thus be either a right-handed Beltrami field or a left-handed Beltrami field, but both have the same wave number. Thus, we need to do something different to make these equations work for an isotropic chiral medium. Let us try to change the constitutive relation. In a simple attempt, let us also use the antisymmetric part R of grad U in the stress-strain constitutive relation, with beta as the chirality scalar. But that simply gives back Navier's equation with altered Lamé constants. So this attempt fails. In the second attempt, let us use the simple antisymmetric dyadic capital X equals U cross I in place of R. Success! Angels blow trumpets. We get a single curl term, but this happiness is short-lived. The tensor U cross I cannot be like a strain because it contains the actual displacement rather than the spatial variation rate of displacement. A drastically different approach is needed. This was supplied by the Cosserat brothers in 1909 in their theory of micropolar solids. This theory requires the displacement vector U and the stress sigma. In addition, it creates a new field vector called microrotation denoted by phi and a coupled stress tensor M. The usual equation of motion will not conserve angular momentum now, for which purpose another equation of motion is needed. And that has J times rho as the inertia per unit volume. But that's not all. There are new constitutive relations as well. Here they are, courtesy of Lakes and Benedict. Wow, wow, wow. See the curls. Also, we had 3 constitutive scalars before, lambda, mu, and rho. Now we have 8 more, kappa, alpha, beta, gamma, C1, C2, C3, and J. Compare electromagnetics and elastrodynamics. For an isotropic chiral medium, electromagnetics requires just one more constitutive quantity. So the increase in constitutive quantities is 50%. In elastrodynamics, the increase is 267% from 3 to 11. No wonder the elastrodynamic characterization of isotropic chiral materials has not advanced, whereas electromagnetic characterization of the same materials began in 1815, albeit slowly, but is nowadays routine. Literature on electromagnetic materials and metamaterials of the isotropic chiral variety is growing rapidly, fed as it is by experimental work on the sole chirality scalar. But literature on elastrodynamic materials and metamaterials of the same variety, the isotropic chiral variety, is embryonic. Let us not forget that J.C. Bose in 1898 published the way to make chiral composites, simply as dispersions of small enough springs in some host medium. I will end by urging experimentalist mechanicians in this group to take up the problem of measuring all 11 constitutive quantities of isotropic chiral composites. I will also urge theoretical mechanicians to create homogenization theories for the same composite materials. Both of these tasks have been accomplished in electromagnetics, but not in elastrodynamics. I hope that you enjoyed curling with me. Thank you. I can take up questions now.